Alrighty, y'all. Today we're taking a look at your homework 2 for Physics 211. And for this video, again, it's probably going to be in two parts, but for this one, we're going to look at our sneak peek questions and the first few problems on the homework relating to 2D kinematics. This is probably also going to be a longer one, so let's jump right into it with some algebra. All right. So first thing that we want to do, question 1, is we're simplifying our expression, which is 2a times b minus a plus a minus b squared. Okay. So I have two terms, well, two larger terms with some bits in between. So the first one I want to do is I don't like having exponents, so I want to FOIL this out. So when I have a squared binomial, I'm just taking a minus b times a minus b. All right, so I'm going to FOIL. And I believe we talked about this briefly, but we can talk about it again. We have f for my front terms, so a times a is a squared. I have my outside terms, so a times negative b is minus a times b. And again, it doesn't matter if it's b times a or a times b. I just like to write my terms in alphabetical order. Right? Then I have my inside terms, so b times a minus a times b. And then my last terms will be negative b times negative b, which is makes the minus cancel out, the negative cancel out, so plus b squared. And then I have two ab terms right there, so I'm going to combine them. I'll end up with a squared minus 2ab plus b squared. Okay. And then I'm just going to carry down the rest of this. So I'll have, oh my goodness, 2a times b minus a plus all of this. Okay. So the next thing I want to do is open up these parentheses. So I'm going to do that by distributing my 2a to each of the terms. So I'll get 2a times b, so 2ab, and then 2a times a, so that'll be minus 2a squared. And again, I'm just going to carry down all those other terms, plus b squared. Now I'm going to combine my like terms. So I have 2ab here and minus 2ab there, so those will cancel out. And then I'll have minus 2a squared plus a squared, which will leave me with minus a squared. And when I write equations, I don't like to start with a negative, so I'm going to bring my b squared to the front and subtract my 1a squared. And that's going to be my simplified form of this expression. Okay. My next problem is asking me to break a velocity vector into its x and y components. So first thing I want to do is draw my velocity vector. There it is, and v equals 10 meters per second. And I know that it's 30 degrees above horizontal, so there's my horizontal, there's my 30 degrees above horizontal. And then I want to use my horizontal and my vertical to make my right triangle. Because on this right triangle here will be my Vx, and here will be my Vy. Okay. And I always want to draw it so that Vx vector plus my Vy vector gives me my resultant. All right, so I have my, when I'm adding vectors, I go tip to tail. And my resultant goes from the beginning to the end. Once I have my right triangle all set up, then I throw a trig function at it. So I write out my SOHCAHTOA. Okay. And I want to set up just any trig function. So I'm going to start with sine. I'm going to say sine of 30 is opposite, which is Vy, over hypotenuse, which is V. And when I'm breaking things into components, I want to remember that the vector that I am breaking into components should always be the hypotenuse of my right triangle. Okay. So now that I have this all set up, I can solve this for Vy. So Vy will be V times sine of 30, because I just have to multiply both sides by V. And then I have my Vy component. Then I'm just going to use cosine. I'm going to throw cosine at it. So cosine of 30. That'll be my adjacent, which is Vx over my hypotenuse. Vx over V. Then again, I can solve for Vx. So it'll be V cosine 30. Now, alternately, I could have also said that this whole triangle, I set it all up, but I can set up my triangle using a different, or I can set up my trig functions using, that's not 30, that's 60 degrees, right? Because I have a 30, 60, 90. In this case, it's a special right triangle, but I also know that all of my angles in a triangle will add up to 180. So if I find this angle and say, oh, this is 60 degrees, and I want to use that one, I can set up everything exactly the same way. All I'm doing is saying sine of 60 would be Vx over V, and cosine of 60 would be Vy over V. Right, it will give you the exact same answer. I just chose to stick with the 30 that we were given, but it works either way. Right, and then if I'm looking at sine of 30 will be 1/2. So this will be V, which is 5 times 1/2. This is probably where you would break out your calculator. Nope, that's flipping my numbers would be 10 times 1/2 equals 5 meters per second. But this is absolutely where you would break out your calculator. Make sure your calculator is in degrees mode, right? Because we can have radians or degrees. But bust out your calculator. I just remember my unit circle, right? So in this case, cosine of 30 is √3 over 2. Right? So my answer for this will be 5 times √3 meters per second. But if you wanted to be fancy and put it in decimal form, it would be 8.66025403784 meters per second. Right? So the problem asked me to break my vector into x and y components. Here's my x component, and here's my y component. And again, if I used my opposite, if I used the other angle, then I would get the exact same result, just instead of sine, it would be cosine of 60 here instead, and sine of 60 here. It would give the exact same results, though. Right. So, moving along, we now have velocity components, and we need a magnitude and a direction. So this is taking the procedure that we just did for this velocity vector and reversing it. So now I have vector components where it's going 20 meters per second in the x direction and 10 meters per second in the y direction. So again, I've lined these up so they go tip to tail, and now my resultant vector I can draw from beginning to end. When I say from beginning to end, that just means the tail of the one that I started with to the tip of the one that I ended with. So if I added x plus y, it would be the same as if I added y plus x, but obviously my triangle will be upside down to the one I have now. All right, and that's going to be my v vector. So now, given this new right triangle, I need to find the magnitude, or the length of this hypotenuse, and the direction. So I'm going to find this angle theta. Well, I'm going to start with the magnitude because we have our good friend Pythagoras to help with that one. Right? We have our Pythagorean theorem where a squared plus b squared equals c squared, or the length of a leg squared plus the length of the other leg squared equals the length of the hypotenuse squared. So I can set that up and say Vx, I can write in normal color, Vx squared plus Vy squared equals V squared. Right. And if I'm trying to just solve for v, then I would take the square root of both sides. And in doing that, I get that v would equal vx squared plus vy squared, all under the square root. Okay. And because I have values for vx and vy, I can plug in 20 squared and 10 squared and then square root it. And if I was really feeling fancy, that would be 10 root 5 meters per second, or decimals gives us 22.3607 meters per second. Right. Then comes the fun part of finding that angle, right? Because we need to somehow define the direction. So we can say that it's some angle from horizontal, or some angle above horizontal. Well, how do we find that? Well, I was halfway through throwing trig functions at this triangle. So let's throw our last trig function at this triangle. I'm going to say that my tangent of theta, right? So SOHCAHTOA, tangent would be opposite. Opposite would be Vy over adjacent, which would be Vx. Okay. And then I have to solve for theta from this. So what I'm going to do is I'm going to take the tan inverse, or the arctan, of both sides, because what that does is it undoes my tangent, leaves me with theta equals, and then it'll be tan inverse of Vy over Vx. So you might see it like this on your calculator. You might also have seen it in math class if you said arctan, right? Vy over Vx, right? These mean the same thing. It's important to know that this is not raised to the -1 power. This isn't 1 over tangent. This is inverse tangent or arctangent. It undoes the tangent operation. Right? Now if I plug in my Vy and Vx down here, I can get a theta, which will be about 26.56505 degrees. Now, the reason I chose tangent, I could have used any of these because I have my opposite, I have my adjacent, and now I have my hypotenuse of this triangle. But I usually like to choose a trig function so that my answer, when I'm plugging things into my calculator, is only based on values that were given by the problem. So a lot of times you will have these kind of cascading problems where you have to use a previous answer in order to solve the next part of the problem. But in this case, we didn't have to do that. Right? I can do tan inverse and have the two values that were given just by the problem statement and use those. I could have used sine, but if I had made any kind of calculation error in calculating my velocity, which I often do, so I may have made a mistake, then that would carry through and would make my theta also incorrect had I used like sine that includes the hypotenuse or cosine that includes the hypotenuse. So I usually like to try to pick one. I try to use tangent when I'm given my x and y components, but it doesn't really matter. You can use any of these. I just caution against it just in case you make a little like algebra mistake punching it into your calculator or something. But it's not that big a deal, especially on this problem because it's only like one step. Okay. And just finishing this off, we were asked for a magnitude and a direction. Just an angle on its own is not sufficient because I don't know, I haven't defined where this angle is to or from. I said it before, but this is going to be 26.6 degrees above horizontal. It's always important that we're clearly communicating what we're actually trying to say with our numbers, right? 22.36 meters per second is the magnitude of my velocity, and 26.6 degrees above horizontal is the direction of that velocity. Moving right along, we have problem 4, which is solving these two equations for y in terms of a, b, and c. So we have y equals ax and, oops, sorry, not x, 0 equals bx squared plus cx. Now, it looks complicated because it looks like we don't have anything, but assuming that we know a, b, and c, given that assuming those are given values, really the only things that I don't know are y and x, which makes this 2 equations and 2 unknowns, which is very solvable in terms of algebra. Now, I will also say there are 4 ways that I can solve this. Right? I can solve this equation first. I can come over here and say that x equals y over a. I divide both sides by a, and then I get this. Then I can plug in over here. Then I'll be solving a quadratic. All right, I'll be solving 0 equals b times y over a all squared plus c times y over a. Right. This is y squared plus c times y, so I'm solving a quadratic over here. And I could solve this quadratic either by factoring or using the quadratic formula. All right, so that's what I call my first 2 solutions, is I solve for x first in this equation and plug into my quadratic, and then I have 2 different ways of solving the quadratic. My other 2 ways I think are a little bit easier. And the way that I would determine which one is easier is because if I solve here, then when I plug into my second equation, I have to plug in here and here. I have to plug in 2 different spots and also square whatever I'm plugging in, which is a little gross and weird, and I don't really want to do that. But if I solve into this one, if I solve for x in this one and plug in over here, then I only have to plug it in once and I don't have to square it. All right, so I think it's a little bit easier to solve for x here first and plug into the other. So let's go through that one real quick. So I can see that these 2 terms have a common factor of x. So I'm going to factor that out. I'll have 0 is, I said I was going to factor that out, b times x plus c. And then when I have these 2 factors, I set each one equal to 0 independently. So I get that x equals 0, and also bx plus c equals 0. Now, obviously I have this one solved for x already, but let's get this one solved for x. So I'll subtract c from both sides. Bx equals minus c. And then I'll divide by b on both sides. So I'll get x equals minus c over b. Okay. Now I have 2 solutions for x to plug into my equation over here. Not this one, plugging into this one. All right, so y will equal a times 0. All right, because that's my first solution for x, which means y equals 0 is a solution. Or I could have y equals a times my other value of x, which we said was negative c over b. And just shuffling things around because I want to open up those parentheses, I'm just going to say it's minus ac over b. So those will be my 2 solutions for y. Now, I said there were 4 ways to do it. I mentioned the first 2, and here's the third. The other one would be, again, solving for x in this equation, but instead of factoring, using the quadratic formula, which will work out to exactly the same answers that I got here, just a little bit more simplification. Plus also I have a, b, and c already used in this equation. So I don't want to try to bust out my quadratic formula and figure out whether like b squared minus 4ac all over 2a8. Right, because my a's and b's and c's in these equations might not line up, and in fact they don't line up with the a, b, and c in my quadratic equation. So just a little complicated. So that's why I chose to factor, because I could also see how this one was easily factorable. All right, so moving on from our algebra, we're doing more algebra. Right, so we're going to use our x of t and v of t kinematics equations, eliminate the variable t, and end up with this as our result. So I'm going to start by writing out our two equations. So v of t is v naught plus at, and x of t is x naught plus v naught t plus 1/2 at squared. Now I'm not writing this with my x or y subscripts because it could be x and x or it could be y and y. I'm just keeping it general because I don't want to write those subscripts every time I rewrite my equation. And I also, I don't want to rewrite all my subscripts, and I also want to keep it like the most general form. So you'll also notice that when we derived this in recitation, we knew that it was like applied to a certain problem where I have a negative acceleration. So what I'm doing is I'm keeping my acceleration positive. I'm not plugging in any numbers anywhere. I'm not assuming that it's negative, because then what happens is I solve all the way to this equation. Once I get here, then if a specific problem has a negative acceleration, I can plug in a negative value for a, but if another problem has a positive acceleration, I could also plug in a positive number for a, and it'll all work out for me. All right, so the first thing I'm going to do is I'm going to solve this equation for t. All right, I know I was just saying that, oh, I have to plug it in twice, so why would I do it like this? I don't want to solve this equation first. It's just not a pretty equation. The other one was easily factorable. This one I would probably have to use like quadratic, all that mess. So we're going to solve this one for t and plug into the other one and just deal with the consequence of our algebra. I'm also going to say, because this equation has v final instead of v of t, it's just a little bit easier to write as I go through. Same thing with x final. So just know, first thing I'm going to do is swap out v of t, just going to equal some v final, and my x of t is going to equal some x final. I'm just going to swap those out for ease of writing things. So I'll have vf v naught plus at. Now if I'm solving for time, I'm going to subtract v naught from both sides. So I'll have vf minus v naught equals at. Then I can divide by a on both sides of my equation, get vf minus v naught over a equals t. All right. Now that I have time, I can plug in to my other equation over here. So I'm going to start by swapping in my x final. Then as I rewrite things, I'll have x initial or x naught plus v naught times time. I swap in my vf minus v0 over a plus 1/2 a times vf minus v0 over a all squared. Now, this may look slightly familiar, right? So I'm going to get this just out of the way. So I'm going to subtract it over. So I end up with just all of this. Now this is something times a binomial plus something times a binomial squared. This should look familiar because that's the purpose of the sneak peek problems. Something times a binomial plus, well, this would just be 1. In this case would be my coefficient, but a binomial squared. So we've done something very similar to this, and we're going to simplify it kind of exactly the same way that we did before. So I'm going to distribute my v naught in over my numerator. So it'll be v naught vf minus v naught squared over a plus, then I can say distribute this 2. This squared can go to my numerator and to my denominator. All right, I can square them individually, because then what I'll end up with is something times a divided by a squared. So that'll cancel out and leave me with divided by a. That 2 can also stay in the denominator because it's in the denominator of that fraction. So I'll end up with vf minus v naught squared, because I brought that in, divided by 2a. Then I don't like fractions, so I want to get rid of my fractions. So I'm going to take this whole each side of the equation and multiply by 2 times a. So I'm multiplying this fraction by 2a and this fraction by 2a. This one will just cancel out, but this one will leave me with an extra coefficient of 2. So I'll have 2a times xf minus x naught equals 2 times v naught vf minus v naught squared. And then the only thing left, right, since my 2a canceled, it would just be foiling this out, which we did earlier. All right, I'll let you look back at that, but it'll be vf squared minus 2 v naught vf plus v naught squared. Now I want to distribute that 2 over to my other terms. So I'll get 2 v naught vf minus 2 v naught squared. And then I would just carry through the rest of my equation. Now, this side, 2a xf minus x naught, already looks like the half of the equation that I want to see. So all that's left to do is simplify this side of the equation into what we wanted to see. So just like we saw before, we have our 2 v naught vf, our 2 v naught vf and our minus 2 v naught vf. So those will cancel. And then I have my minus 2 v naught squared plus v naught squared. So that'll leave me with my v final squared, which I just carry down from here, minus my v naught squared. And I'm just going to bring down that left-hand side, 2a x final minus x naught. Right. And that's how I get to this equation here. Right. Now that we have derived our third kinematics equation, and we have 1, 2, 3, we can use that whenever we see fit. A lot of times when we're looking at these problems, we'll see that based on the variables that I know and what I'm trying to find, some of these equations will be better, and some of these equations will be better in certain situations, and some won't be as helpful. Right? So let's start applying some of these kinematics equations. We have an excellent dog named Walter, who is learning about two-dimensional motion. Right? So first thing I want to do for a kinematics problem is draw a picture of what's going on. So we're out on the quad, 20 meters apart, and Matt throws the ball directly to Walter at a given angle. So what that tells me is here they are, 20 meters apart. Here's Walter. Here's Matt. And when Matt throws the ball, he throws it at some angle. All right, so here's my initial velocity vector. And we're given that it's 55 degrees above the horizontal. I mean, you can see that I kind of wrote this in. It said 50 at one point. I may have had an old version of it. If my numbers are slightly different, the procedure is exactly the same. Okay. So now that I have my initial velocity drawn, we can kind of imagine the trajectory of the ball. Not really necessary. But the next thing that I have to do after I draw my picture, I have to set my coordinate system. So I'm going to draw my origin there, and I'm going to say positive x is that way and positive y is that way. So I've drawn my picture, I've visualized my problem, I've set my coordinates. The next step before I even look at what is being solved for, I want to make sure I have this vector broken up into components. So I redraw my vector so it's a little easier to see. There's my v naught. I draw my v naught x. I draw my v naught y and my 55 degrees. Now that I have my right triangle, I throw a trig function at it. So sine of 55 will be v naught y over v naught. So v naught y will equal v naught sine 55. And when I throw cosine at it, I'll get that v naught x equals v naught cosine 55. All right, we've talked about this a fair amount, so I might start moving through my vector components a little bit quicker. But just know, all we're doing is throwing, so katoa We don't have to try to figure out which trig function will be most helpful because there's only 3 that we can use. So use one of them, see if it's helpful, and then use another one, see if it's helpful. Right? So, all of this to say that we're trying to solve for what speed did Matt have to throw the ball at for Walter to catch it. So, my next thought is, now that I know generally what I'm thinking about solving for, I want to think about what do I know, because that will lend itself a little bit to how to select equations and stuff. Right, so x naught, x of t, v naught x, v x of t, ax t, and y naught, y of t, v naught y, vy of t, ay, and t. These are all my possible variables, and I want to think of which ones am I solving for, which ones do I know, which ones do I have to figure out in the meantime. So when we're asked, what speed did Matt have to throw the ball at for Walter to catch it? What I'm solving for, I'm thinking about what is the value of v naught, right? That's my first blank, because what speed do I have to throw it at? What speed, what is my initial velocity so Walter can catch it, right? So what is the value of v naught? And when I'm solving for one of these initial conditions, I want to think, what is the value of v naught so that my end result happens? What is the value of v naught so that the boot makes it over the river? What is the value of v naught so that Walter catches the ball? But now we're thinking about Walter catching the ball, but we have to think about that in terms of what variables I'm going to use to define that happens. So what is the value of some initial condition so that Walter catches the ball? Well, how do I know Walter catches the ball? Well, first of all, it has to land on top of Walter, and it has to be where he is. So I know it has to be where Walter is, but it also has to be landing at that time, because if it's sailing over his head, then something else is going wrong. So I want the value of x of t, right? I want it to be where Walter is, equals that distance 20 meters at the time when y of t equals 0. So this says that at the time when y of t is 0, so when it's going to hit the ground, I want x of t to be 20 meters, so it's kind of landing right where Walter is. And I need to figure out what initial velocity causes that to happen. So now embedded in this question, in this sentence, is kind of a roadmap of how to solve the problem. The first thing I need to figure out is the time when y of t equals 0. Right? So if I'm coming down to set up my equation, y of t equals y naught plus v naught y t plus 1/2 ay t squared. I want to set that equal to 0. I'll make a note to myself. I'm going to solve for t. Right? Then I want x of t to equal 20 at that time, which means I'm taking that time that I solve for and plugging it into my x of t equation. X naught plus v naught x t plus 1/2 ax t squared. Right? And plug in. All right. So this is kind of my roadmap for the problem. I just have to, since I'm trying to solve for v naught, I have to make sure that v naught is somewhere in one or both of these equations. So let's visit what variables we know and what we don't know, and what do we not care about. So because of how I set my coordinates, I know that my x naught is 0 and my y naught is also 0. We set my x of t. We said that was going to be my 20 meters. Right? And my y of t, we said that was going to be 0 as well. Right? That was what we determined when we were writing that sentence. My v naught x, well, I have that. I don't know a number for it, but I have it in terms of v naught. So that's how I can incorporate v naught into these equations. So I can have them, my components here. So it'll be v naught cos theta. Well, that theta is going to be 55. I'm just going to write theta. And this will be v naught sine theta. So that's my easiest way to incorporate the variable that I'm solving for into the equations that I'm solving. All right, my final velocity, well, I don't know it and I don't really care about it right now. And remember that my final velocity, we can't call it 0 because even though it hits the ground and it might stop moving, we're really thinking the instant before it hits the ground, because once it hits the ground, there's a bunch of other forces and stuff, and my acceleration is no longer constant. So once it hits the ground, all of these equations no longer apply, so we can't just assume that our final velocities are 0. All right. So I don't know that, and I don't really care about it right now, so we can just ignore those. But I know my x acceleration for an object in free fall will be 0, and my y acceleration will be minus g. And the reason it's minus g is because gravity is down, and I said that up was positive. Okay. So all that to say, I have a fair bit of information about these equations. So I know that I want to set this one equal to 0. So I'm going to plug in everything that I know. I know my y naught is 0, so I'm just going to skip that if that's all right. I'm going to go v naught y was v naught sine theta times t. And that'll be plus 1/2 minus g t squared. This is my first equation that I said I was going to solve for t. Now this should also look familiar, because this was also in our sneak peek problems. I had something x squared plus something times x. Well, now I have something times t squared plus something times t. So same exact thing I did before. I can factor out t and say that v naught sine theta minus g over 2t equals 0. And it makes sense, right, that t equals 0 would be a solution. That's telling me that when time equals 0, y of t equals 0, which makes sense because we said that y naught is 0, which is y of t at time equals 0. So we can kind of ignore that solution. That's not our useful one in this case. And we can use this solve here. So I'm going to set this term equal to 0. So I'll subtract v naught sine theta to the other side of my equation. So it'll be minus g over 2t equals minus v naught sine theta. Then I'm going to divide over g over 2. So my negatives will cancel. And really, I'm multiplying by 2 and dividing by g. So t will be 2 v naught sine theta over g. Now that I have t, I'm plugging it into my x equation, set equal to 20 meters. Okay. And again, my x naught, we said that was 0, so I'm going to skip that part and say, okay, my v naught x was v naught cos theta times t, we said was 2 v naught sine theta over g plus 1/2 ax. Well, we said ax was 0, so that's going to make this whole term go to 0 anyways, which means I don't have to plug in this gross thing into here, square it, and then simplify. All I have to do is take this term here. That's my only remaining non-zero term, and I'm setting that equal to 0. Sorry, equal to 20. Now I'm taking this equation and solving it for v naught. So I have all multiplication and division. So I can take this v naught and my v naught there, it'll become a v naught squared. So it'll be 20 will equal, and I'm going to pull out everything that's not v naught squared off to the side. It'll be cosine theta times 2 times sine theta all over g. Now all I have to do is solve for v naught. I can take this whole thing and divide it to the other side, which again will just be like multiplying by g and dividing by all of this. So it'll be 20 times g over 2 cosine theta sine theta equal v naught squared. And then I just have to get rid of that squared. So I'm going to take the square root of both sides of my equation to get rid of that. So here is my expression for v naught. I did all that algebra. I didn't have to write any gross decimals. I didn't have to carry any numbers through or mix up any of my calculations. Because now all I have to do is plug in all of my numbers right here. And when I do that, I'm plugging in 55 for theta and 9.8 for g. You can use 10 as well if you want. You could use 9.81, whatever boats you float. 14.4496255,647 meters per second. My units are important, right? It's a velocity, measure in meters per second. And all of my units at the beginning were already given in base units, so we can just carry everything straight through. Right. So I found my initial velocity so that Walter catches the ball. There's part A. Part B, how long was the ball in the air? Well, in this one, we're solving for what is the value of time when it lands, right? My time duration for how long it takes to land, what is the value of time when it lands, and how did we say that it landed? What is the value of time when y of t equals 0? So we already have that. We set y of t equals 0 and solved for time. We just couldn't get a number before because we didn't know v naught. Fortunately, that's not an issue anymore. So what I can do is I can just plug in, same thing I did before, plug in g of 9.8 or 10, right? And plug in a theta of 55 and plug in my v naught of 14.45. The only other thing that I will add is that g on its own is a positive number. So I will say, I'll write it over here, that g equals 9.8 meters per second squared. G does not equal negative 9.8. The way that I account for the negative is based on my coordinate system. So in general, we assume that g is positive unless we give it that negative sign out in front. And that negative sign out in front comes from the fact that I said that up was positive, so I have to say my acceleration is negative g. Right? Gravity is not inherently negative. So when I plug in my positive g value, because I already counted for the sign, my initial velocity, and my theta, I'm going to end up getting 2.416 seconds. So how long was the ball in the air? 2.416 seconds. I should circle this as well. Okay. So our next section, how fast was the ball traveling at the apex of its flight? That's an interesting question, because now my t is different. Because remember, this was t when it landed. So now I have to figure out how fast was the ball traveling, or what is the value of velocity, right? How fast, velocity, when it was at the apex of the flight. Well, how do I know it's at the apex? Well, the apex is where it switches from going up to going down, right? It's still going to the right, but it switches from going up to going down. So somewhere in there, my positive y velocity is going to decrease until it gets to 0, and then it's going to start going in the negative direction. So how do I know that I'm at the apex? It's when it switches direction. So it'll switch direction when Vy of this new t, I'll call it TA for t apex, equals 0. Okay. So how fast was the ball traveling at the apex of the flight is what is the value of v at the time when Vy equals 0. Vy of t equals 0. And that also enters another interesting point, that since my y velocity is 0, my net velocity vector, my v, will only have an x component. So if I solve for Vx, that's the velocity. That's how fast it's traveling at the apex of its flight. So I just have to solve for my x velocity because my y velocity is 0, and I don't have to do my Pythagorean theorem to put the vectors back together because one of them is just 0. Okay. So what I have to do is I have to set up my equation, right? So Vx of t equals v naught x plus axt, and I'll set up my Vy equation as well. Vy of t equals v naught y plus ayt. And now I'm just going to blindly do the algebra, set this equal to 0, solve for t, and then plug on it. But we made one little lapse. My acceleration in the x direction is 0. So this whole term goes to 0, and it doesn't matter what time it is, my x velocity is just the initial x velocity. So I could solve for the time that it takes to get to apex, but I wouldn't have anywhere to plug it in to my equation, because my x velocity is always the same. So it's an important thing to note that we're at apex when my velocity is 0, and that means that the velocity at apex is just the x velocity. So that was an important conversation to have, these two things. But we don't need to actually do the math to get the time to apex because it doesn't change. So that being said, my Vx of t is v naught x, which we said was v naught cosine of theta. I can plug in my v naught, I can plug in my theta, and my x velocity, or my velocity at apex, because again, the only velocity I have is that x velocity, will be 8.2873 meters per second. Okay. Now, our last one. Suppose that his arm moves through a distance of 80 centimeters while pushing the ball. First thing that I want to do, I don't want this in centimeters, so I'm going to convert it to meters. So I'm going to say 80 centimeters. And then I can say for every 100 centimeters, I have 1 meter. My centimeters cancels, I'm left with meters. So 80 divided by 100, that's 0.8 meters. Okay. So distance of 80 centimeters, or 0.8 meters, while pushing the ball forward, what acceleration will we have to impart to the ball? So I'm accelerating the ball. Now this is a whole different problem. None of my variables over here apply. I'm accelerating the ball from rest to my initial velocity that I needed for the start of this problem, because this one's happening beforehand. So now I know my initial velocity will be 0. My final velocity will be that 14.45 meters per second, because whatever I end up with here is what I'm going to start the next chunk of the problem with. And I know that my change in position, I'll call it S, right? That's my 0.8 meters. And I'm trying to solve for acceleration. So I know my initial and final velocity, I know my change in position, and I don't know my acceleration. This seems like a golden opportunity to use our new kinematics equation. Vf squared minus v naught squared equals 2a, I'm going to say delta s, just means change in position, same way that delta x would, right? I can say x initial, x final, right? Delta just means change in, right? I'll write that, x final minus x initial equals. Okay. So in this equation, right, I know everything except for A. I know delta S, I know my two velocities. So it's just one equation, one unknown. So solving for A, I'm going to divide by 2 and divide by S. So it'll be V final squared minus V naught squared over 2 delta S equals A. Then all I got to do is plug in my numbers. I plug in 0.8 for this. I plug in my 14.45. I plug in 0. That'll give me an acceleration of about 130.5 meters per second squared. Now that's much higher than gravity, which is 10. It's about 13 times gravity. So that was the thing that we did in our last homework, was comparing the acceleration that we calculated to gravity. It's accelerating over a pretty short distance, so I would say that's fine. Again, as long as it's not completely outrageous, like we're not accelerating past the speed of light, then I think that's fine. All of the numbers that I'm giving you for these problems, I just threw into my calculator once. I will say there is a possibility that my numbers are wrong, but my procedure is correct, right? So if there's ever a question of you getting a different answer, but you did the same procedure, I would trust your answer. All right, we'll do one more for this video before we call it. We have our dog named Teddy, and he's jumping out onto a lake to land on top of a ball. First thing again, kinematics problem, I'm drawing a picture of my problem. I have a distance d to the ball. I have a height that we were given, but let's call it h. And I know that my initial velocity was horizontal. These are all things given by the problem. So I draw my picture, and then I'm going to set my coordinates. I'm going to put my origin there, say that's positive y, that's positive x. Right. A lot of times I like to put my origin at the leftmost and downmost point in my problem so that right and up can easily be positive and I avoid negative numbers if at all possible. Right. Next, I'm thinking about my velocity broken into x and y components. Because it is just horizontal, right, I can say that my v naught equals my v naught x and my v naught y equals 0. Right? This vector does not have a component. It is not going up or down at all. It does not have a y component, so we say it's 0. Then I want to think about what am I going to solve for? So how fast was Teddy moving when he left the platform? Well, what is the value of v naught? How fast are we moving? And how do I know that it's the right v naught? Well, we're told that he lands on top of the ball. Same thing we said before. He lands and he's on top of the ball. So how do I know that he's on top of the ball? My x of t will equal that distance d, which I think is 7 meters. Yes. All right, so how do I know that he's on top of the ball? His x of t is d. And how do I know he's landing? My y of t will be 0. So what is the value of v naught so that so that x of t equals d at the time when y of t equals 0? So again, I'm going to write down all the things that I know. My x naught, my x of t, my v naught x, my vx of t, my ax t. X naught is 0 just because of where I set my origin. He's starting at the edge of the dock. X of t we just said is going to be d. V naught x is v naught. Vx of t we don't really care about right now, so we'll just skip past that. And ax is going to be 0 because he's in free fall. Then I have y naught, y of t, v naught y, vy of t, ay and t. Y naught in this case is not going to be 0 because I'm starting above my origin. My y naught's actually going to be that h, or that 2 meters. But my y of t we said was still going to be 0. My v naught y we said was 0. My vy of t, again, we kind of said we don't know and we don't really care about right now, so we can leave that. And again, since I said up was positive, my acceleration will be minus g. So first thing I want to do, find y of t equals y naught plus v naught y t plus 1/2 ay t squared equals 0. All right. And the reason I'm using my position equations instead of any of the other ones, again, because I don't know and I don't really care about that v final as of right now. So setting that equal to 0, my y naught is h, my v naught y is 0, and my acceleration is minus g t squared. So if I'm solving for t squared, then I'm going to subtract h to the other side, multiply by 2, divide by g. So t squared. And then when I multiply and divide my negatives over, the negative will cancel. So it'll be 2 times h over g. Okay. And then to solve for t, because I don't need t squared, I just need t, it's going to be 2h over g. Okay. Now, that's the time when he lands. So we have to just make sure that at that time when he's landing, my position is what it should be. So I'm going to say that my x of t equals x naught plus v naught x t plus 1/2 ax t squared equals d. Again, we said my x naught was 0, and my ax is also 0, and my v naught x, that's just v naught. And I just have to plug in my t, which is the square root of 2h over g. Set that equal to d. Now all I'm doing, I'm solving for v naught because that's what the question was asking me for. So flipping things around, I can divide my fraction to the other side, which will just flip it. So v naught will be d times the square root of g over 2h. Right? Then all I have to do is plug in my numbers. D is 7, G is 10 or 9.8, and H is 2. So what that's going to spit out, 10.957 meters per second. Again, saying that D is 7 meters and H is 2 meters and G is 10 meters per second squared. It'll all it'll work out to meters per second if you check those units. That's a bonus fun practice for you, is check the units on that one. Next, how fast was Teddy moving when he landed in the water? Well, now, how fast is he moving? Now I'm considering my Vx and Vy. Right? So I want to know, what is the value of V? What is the magnitude of my velocity vector when he landed in the water at the time when y of t equals 0? Fortunately, we already have the time when y of t equals 0. So all I have to do is plug that into each of my velocity equations. So Vx of t equals v naught x plus axt, and Vy of t equals v naught y plus ayt. And I just have to plug in my accelerations, my times. Right, so my initial velocity in the y was 0, but my acceleration in the y was negative g. So I know that my Vy of t will be negative g times the square root of 2h over g. And my acceleration, the x, was also 0. So I don't even have to plug in time for this one because it got canceled out. But my Vx is just going to be my v naught x, which was just v naught. Right? So again, I just have to plug in my numbers. Obviously v naught x being v naught, we just solved for that one. That was our 10.96 meters per second. And then I have to plug in all of this. Now this negative g out in front, will give me that this is a negative 6.261 meters per second. And all that tells me is because I said up was positive, that means that my y velocity is going down. So when I draw my vector, I have a positive x velocity and I have a negative y velocity. Right? Vx, Vy, and my resultant going down this way is V. Call that theta. And now if I'm solving for how fast he was going when he hit the water, I'm solving for that magnitude of V. So we can use Pythagorean theorem again, where V will be the square root of Vx squared plus Vy squared. And that's going to give me a magnitude of about 12.619 meters per second. And the last part of this question is what direction was Teddy moving when he splashed into the lake? And we remember that we have to give our answer in a physically meaningful way. So we can't just say this many degrees. We have to specify where that angle is. In this case, the angle that I've drawn is below my horizontal, below my x direction. So again, solving for that theta, I can use any trig function I want. I'm going to use tangent. So I'm going to say tan theta is opposite over adjacent, Vy over Vx. And like I did before, I take my inverse tangent of both sides of my equation. So I'll get theta is tan inverse of Vy over Vx. And remember, that's the same thing as saying arctangent. Then all I have to do is I have to plug in my x and y components. When I'm punching this into a calculator, I want to just punch in the magnitudes of my Vx and Vy, because a calculator will get confused if you try to plug in a negative inside. It's not as smart as we are. So we've already accounted for the fact that it's below the horizontal instead of above the horizontal. So what we want to do is we want to plug in a positive, so it'll be tan inverse. My positive, that's 6.26 for my Vy. And then, again, my positive, 10.96, but that was already positive. Right? Because all I want from my calculator is the angle. I don't want it to try to interpret if things are up or down from the horizontal. But when I punch this into my calculator, it'll give me an answer of about 29.745 degrees. So if I were reporting this answer, I would say it would be 29.745 degrees below horizontal. Right. So that's where I'm going to leave it for part 1 of your homework. Let me know if you have any more questions about this or anything else you want me to try to explain. And I'll do my best to try to explain it, because I guess Sydney explains stuff.